So in previous class, we did the concept of the gravitational potential and gravitational potential energy. Right now, we have to understand the concept of the kinetic energy. Okay. Um, okay. So kinetic energy. Okay. So we know that the kinetic energy has two different formulas. Okay. Okay. So kinetic energy is basically the movement, sorry, energy stored in a body due to its movement in a mass, would be better word, mass due to its movement. Okay. Movement. Okay. So, okay. So the general formula for the kinetic energy is like half mv squared, right? But if we if we consider the kinetic energy with in term of the position, so we know that the velocity in any orbit, velocity in any orbit is given by v is equals to gm over r, or v square is basically gm over r, right? And if you want the derivation, so the derivation is very simple, right? In the Kepler's law, we did that. Okay. Where we say Fg provides the centripetal force to the object mr omega square. Okay. And sorry, mv square over r, not over r. Okay. And Fg is going to be gmm over r squared is equals to mv squared over r. Okay. So r and r simplifies. Okay. So we are left with v is equals to gm over r. Okay. This is v squared, right? So this is basically the velocity of the object in a specific orbit. Okay. So let's say that I have the planet. Okay. I have this planet right here. Copy and paste. Okay. So this is the planet. Okay. And object is moving around a planet. Okay. Let's say this is the, sorry. Okay. So let's say this is the circular path around around the planet. Okay. And an object is moving in it. Okay. An object is moving in it. Okay. With some velocity. Okay. And the velocity is given by v square. V square is equals to gm over r. Okay. So this is the velocity. This is basically the orbital velocity of the object, right? So, yep. Now, if you put that back into kinetic energy formula, then you will get the actual kinetic energy in terms of position. Okay. So the kinetic energy is going to be um, GMM. Okay. GMM, come on. GMM over 2R. Okay. If you place the V square value in the actual equation, okay, this over here. So you'll get this formula. Okay, this is the concept of the kinetic energy, right? Now, if you want to find out the change in the energies, then you can just subtract the two energies, you'll get the change, right? Um, and moving on to the total energy. So for the total energy, um,
Sir,
mhm,
I don't understand the key thing. Like, could
okay,
you explain?
okay, just give me a second, please. Um, Total energy. Okay, yes. So basically, in kinetic energy, the basic formula for the kinetic energy is half mv squared, right? And if the velocity is given to you, then you have to use this formula. But if the distances are given to you, then instead of this formula, you can use this formula, okay? Right? This is basically the formula for the kinetic energy in term of the position, okay? Right? And this is that position that I'm talking about, okay? Okay, this is that position R, right? And if you want to know that where does this V come from, so we basically use the Kepler's law where we said that gravitational potential, gravitational force provides centripetal force, okay, to the planet, and then we start solution, okay, getting?
Yeah.
And that's it. This is a simple concept. And after getting this V square is equals to Gm upon R, I just put the V square in its value. Okay, so I got this thing. Okay,
Oh, okay, okay.
clear.
Yeah.
So now talking about the total energy. So total energy at any point is going to be the same, right? If you don't have any resistive forces, if the resistive forces are there, then the total energy will going to decrease. Okay. So, but the total energy of any system uh, is given by the sum of the kinetic and potential energy, right? So total energy is basically sum of kinetic energy plus some of the kinetic and potential, yeah, or gravitational potential energy. Okay. Now, if we consider the kinetic energy and the gravitational potential energy formula for the total energy, so let's say the total energy ET and the kinetic energy is GMM over 2R. Okay. Plus the gravitational potential energy has a formula with a negative sign over R. Okay. Right. If you try to subtract the two quantity because you have the negative sign, you have to take the LCM first, right? So taking the LCM, okay. So after taking LCM, I should get two here and two here, right? And then I can simplify total energy as negative Gm over 2R, okay? This is the formula for the total energy, right? And this only contains the gravitational potential energy and the kinetic energy, right? So we can say that if the loss in the energy caused by the resistive force, okay, caused by the resistive force, then total energy will going to be will going to be smaller than its value. Okay, because you are not considering it. Okay, so these are all the concept of the energy. Now, we have two more concepts remaining. Okay, one is the escape velocity concept, and the other is a graphs for the gravitational potential. Okay, so but before that, I'm just taking a break for namaz. Okay, and then I'll be back in like 10 to 15 minutes. I'll continue. I'll try to complete the class around around 7 my time, 6 your time. Okay. So let's see. Okay. Just be in the meeting. Okay. As soon as I get back, I'll text you guys to get back and we resume. Okay. So we discussed the concept of the total energy as well. Okay. Now let's talk about the escape velocity. Okay. And this is one concept regarding or this is one concept that is related with the total energy, right? And the concept is the concept of the escape velocity. Okay, we have escape velocity. Okay, so escape velocity is basically the velocity with which something, if you launch something, so it can go into the outer space. It can, I think I missed the E in it. Uh, there should be E in it. Okay. No, the E is already there. Okay. So escape velocity. Okay. So this is basically the velocity. Okay. Or it is basically the initial velocity. The initial velocity with which the object is launched such that such that it just reach the infinity. Infinity. Okay, infinity means where the gravitational field strength of that planet goes to zero, and it just overcome the gravitational field strength. Okay, so the this is the concept of the escape velocity, right? Now let's assume that if I have the planet, okay, let's say I'm considering this planet, copy and paste. Okay, paste. Okay.
How does it how does it get like launched if it's still in a gravitational field?
Like the rocket, if like you're
Oh,
on the earth, okay, and you want to launch it such that it can overcome the gravitational field strength of the earth and it go like beyond the field, okay, into the space, right? Getting
yeah, okay, okay.
so so okay, so let's say I have the object right here. Okay, so I have the object right here which I want to launch. Okay, which I want to launch in the space, okay, say that it just reach the infinity, okay. So this is the concept. Now let me, okay, this is the object that we are launching, okay, with the initial velocity, with the initial velocity v called the escape velocity, okay. So VES. Okay, so this is the initial velocity of the object, right? Now, let's consider that this distance is the infinity, okay. Okay, so The distance to this point is d is equals to infinity. Okay, you can take d or you can take r, up to you. Okay, now if we apply the law of conservation of energy, so we know that the total energy at any one point should be equal to the total energy at another point. Okay, so whatever the total energy at this point should be equal to the total energy at that point, right? And over here the total energy is only in the form of kinetic energy, and the total energy over here is only in the form of gravitational potential energy, right? So we can say that, or we can rather equate the kinetic energy with the gravitational potential energy, right? So over here, Ke is the only form of energy, right? Ke will be maximum, okay? And Ke will be maximum, and GPE will be of some value, right? And at that point, Ke will be zero, right? Because we are saying it's just reach infinity and it lose all of its energy, right? That's why we are saying it is just reaching infinity, right? By losing all of its energy, and GPE will going to be maximum. Okay. Now let's just put in the law of conservation of energy for the calculation. Okay. So initially we have the total energy in the form of kinetic plus GPE, right? And finally we have the energy in the form of kinetic and GPE, right? But we know that final kinetic energy is going to be zero, right? Because all the energy, all the final and all the initial energy converts into gravitational potential energy and no kinetic energy left. Okay, and that's why we are saying it is just reaching infinity, right? But initially the kinetic energy is given by half mv squared, and since we are interested in the escape velocity, that's why I'm using this formula and not the other one which we just derived. Okay, and plus the gpe is going to be negative gmm over r. Okay, and r is going to be this distance. Okay, r is going to be this distance. Okay, this is the r. Okay, and the total distance is, let's say, is capital R. Okay, so is equals to, finally the kinetic energy is zero and the gravitational potential energy is going to be minus gmm over, we know that this is actually at infinity, right? Because we are working at infinity. Okay, okay, so 1 over infinity gives you zero, so this also goes to zero, right? So you'll be left with the only two things, that is half mv squared is equals to gmm over r, right? The negative sign goes off. I just took this whole thing to the other side. Okay, now m and m goes out, and we are left with v square is equals to gm 2 gm over r, right? Is that clear? Is the concept of the escape velocity clear? Acha, by the way, the derivation is not a part of the syllabus. Only you need to remember this formula. Okay, so if you understand this formula, then it would be enough for you. Okay. So let's say if you have the object of if you have the Earth and the rocket, which you want to launch it to the infinity. So you just need to put in the mass of the Earth, and you just need to put in the mass of the radius of the Earth, right? So basically, for every planet or for every mass, the escape velocity is going to be constant, right? It does not depend upon the object. It does not depend upon the thing that you're launching. Okay, so point to be noted. Okay, so. Escape velocity. Okay. Escape. Let me know when your class starting. Okay. If it is started, then
It's
we.
uh it's
Yes.
supposed to start right now.
Okay.
I
Just.
can write this point and then leave.
Okay. Okay. I'm just ending. Okay. Escape velocity um is specific specific with specific planet. Okay. And it does not depends upon the it does not depend upon the um क्या चीज़ है the object launching object okay launching object okay so yep that's it we'll do graph tomorrow and then we'll do the questions tomorrow okay sure
Okay.
okay take care bro love is
Left is
yes